In theory, we find that the exponential utility function is a good approximation for risk-averse decision makers' utility function. Because most of us are risk-averse, the exponential utility function is a good approximation for most of us. In the exponential utility function, we have u in terms of payoff x equal to 1 minus e to the order of negative x over r. The value of r represents the risk-averse preference level of each individual decision maker. Because we are all different, the r value could be different from each other. For example, r value could be equal to 100, 200, or 300. Normally, the smaller the r, the more risk-averse we are. For every decision maker, actually, we can design a game trying to figure out what is the r value. In this game, we are going to suppose we are in the case of the following with two decisions, A and B, in the states of the nature 1 and 2, and we have a chance to have 150,000 if we use decision A in states of nature 1, and so on. And we are going to have two choices. The first choice is we are going to win Y with probability of 0.5, or we are going to lose half of the Y with probability 0.5. And we are going to increase the value of Y from 0, 1, 2, 10, 20, 30, 100, 200, like that. You want to keep increasing from 0 until at some point you are indifferent of these two choices. I mean, winning Y with 0.5 or lose half of the Y with 0.5. And you don't want to increase the Y value anymore, because if you increase the Y value, you feel insecure and it makes you scared of the game and you don't want to play. So I'm going to suppose you find such a Y value that you are indifferent of these two choices. And for my case, I can assume I have R equal to 100. Right now, everything will be in the measurement unit of K, so that for the first decision A in the state of 1, we have 150,000 in the payoff. If we use the utility function of the u x equal to 1 over e to the negative x over r, we are going to replace the r with 100, and we have x equal to 150, so that we can compute for the decision A in state of the nature 1, the utility u in terms of 150 will be equal to 1 minus e to the order of negative 150 over 100. After computation, we get 0.7769 for decision A in state of nature 1. Similarly, if we plug in x as negative 30 into the utility function of u x, we are going to get 1 minus e negative 30 over 100. After computation, we are going to get negative 0.3499 as the utility for decision A in state of nature 2. And we keep it doing, we get the utility for decision B, 0.5034 for state of nature 1 and 0.3297 for state of nature 2. Given that we have the probability of 0.5 for state of nature 1 and 0.5 for state of nature 2, we can compute for the expected utility value. For example, for decision A, we have 0.7769 times 0.5 plus negative 0.3499 times 0.5, we get 0.2135. For decision B, similarly, we get 0.4165 as the expected utility value. Comparing the expected utility value of decision A and B, we can find that the decision B will give us a higher utility. So we choose decision B over decision A. And you can find that actually, if you use utility, you are going to have decision B as your optimal strategy. But if you use EMV, you are going to have your decision A as your optimal strategy. So you can see that actually your psychology effects plays a role in your decision making. Just now, I assume an R value equal to 100. Actually, you might have different R value in your case. And if so, you can plug in your R value and you figure out your utility table. And you can find your optimal decision based on the expected utility value. Please note that in your homework and quiz and final examination, the R value will be given to you. Thank you.